All right, I'm going to look at our first application here. This is a nice application. It starts taking some of the calculus and really giving us a flexibility we haven't had before. Let me draw the function that we're going to look at here while I tend to try to explain this. Okay, I'm going to curve in. Oops, let me change color here. Make this blue. This is a fairly symmetric function. Don't rely on my weird drawing to come across. Um, and I'll talk about the concept. We can define certain shapes. Um, we'll have machines to make shapes, and if you're having a machine that grinds out, let's say, a lens, the way it moves across the surface, you can trace into how it moves in X and Y and Z. And so we'll look at functions that will be able to create things for us. We'll be able to machine things. And a lot of in physics, we have properties that deal with how we interact with surfaces. A lens is a good example, and the book's going to use this as a lens. And what they're going to talk about, if I'm given a point on a surface, for right now I'm going to label this, but we'll talk about the label in a little more detail. Well, we'll have a tangent to that point. Let me get something that actually looks like a tangent line. And at that point, the tangent line also has something that makes a right angle to it. And this is fairly important in physics, this right angle, that it gets a name. And it's called the normal line. And I think fundamentally, if you've had a physics class, but if you haven't, pay attention when you have them. You're going to have to deal with normal lines often. And in a normal, I think we first really see them when we have some object of a mass moving down a slope, right? So it moves down this slope. There's motion down the slope. And we look at the forces involved with it. And so gravity is pulling straight down, right? That's the force of gravity, which shows the mass times the constant of gravity. And so the concept of the normal comes into place here, where the block surface is going to interact, and Newton's third law says there's an equal and opposite interaction, but the interaction it's having is only along this line. Right? There's a component of gravity that forces with the surface, and it causes an equal and opposite reaction to the surface. If we think really, really close, and if we're looking at the surface here, or any surface, if I have something that's moving in this direction as it comes in, when it comes to the surface, its interaction with the surface, because of Newton's equal and opposite interaction, all of the motion here has no component in the surface. You can imagine a column of stuff right below this that the downward motion gets opposed to, and this gets an upward motion, and so it bounces back off, and these angles end up being equal. Right, the angle of incidence and reflection. Same thing happens with surfaces with glass for very similar mathematical reasons. The principle of least action comes into play, and a lot of complicated systems, we can focus on what's happening at a right angle or parallel at a point. And so knowing that, even with complex shapes, starts giving us a lot of power. And so what we want to do then is find a normal. So we've been finding tangent lines, right? The slope of a tangent line, slope of tangent, is going to be dy dx. And so the normal, or at a right angle, well, it's going to be perpendicular. And so our definition of perpendicular, so the slope of the normal line, I'll use an n for normal, is the negative 1 over the slope of the tangent line. So we have the information now that we can find a little more complex interactions. And so I think the book kind of uses this example, and it talks about the in terms of lenses and why it's important for normals and lenses. This shape here is called the folium of Descartes. It's a kind of well-known curve. You'll see as you learn more and more calculus, there's certain curves that find some their relationships become important for understanding other relationships. But as people were exploring these, they tended to name certain symmetrical curves. This comes from a cubic. So it's cubic in x and y. And so if we want to find dy dx, to find the normal in this, then what we're going to want to do is we're going to want to take the derivative with respect to x of the entire relationship. And so I'll apply this operator to each term. I'm just going to go term by term here. So the derivative of x cubed is 3x squared. We took the derivative of x with respect to x. This will become a 1. The derivative of y is 3y squared. We took the derivative of y with respect to x. Here I'm going to pull this out. I'm going to have a product rule coming about. So I'm going to have the first times the derivative of the second plus the second times the derivative of the first. And then equals 0. The derivative of 0 is 0. So I've applied my implicit derivation to each term. And I'm going to make my dx's over dx's 1. Again, and I'm going to multiply the 9 through. Oh, yeah, and I think we're looking, right, if we want to find the tangent line, we're going to be looking for it at this point, 2 comma 4, the tangent and the normal line. So I'm going to bring my dy dx stuff over to the left-hand side. So 3y squared minus 9x dy dx, right? Because that's a dy dx term, that's a dy dx term, so that'll stay on the left-hand side. Then in the other things, I'm going to take 9y, add that to this side, minus 3x squared. And do my division. And we have a relationship to find the slope. And since I'm looking for the slope at 2 comma 4, we'll evaluate this. At 2 comma 4, which is equal to 9 times 4 minus 3 times 4 over 3 times 16 minus 9 times 2. Or (36 minus 12 over 48 minus 18. (24 30ths) or 8/10. 8/10, 6. I can divide by 6, yeah. Sorry, I was doing a quick division. If I divide by 6, I get 4/5. So, at the point 2 comma 4, our slope is equal to 4/5. So our tangent line, y minus y1 equals mx minus x1, or y minus 4 equals 4/5 x minus 2. Y minus 4 equals 4/5 x minus 8/10. And then I'll continue to solve. Y equals 4/5 x. I'm going to add 4 to both sides. 4 is 40/10, so 32/10, or let me just write it out. Plus 40. Did I miss a number here? 4/5 minus 2 is, oh, it's not tenths. What did I do down there? See, this is why I hate recording videos. You guys can look me with a little slide eye when I do bad mental maths because I'm not running to the calculator. 4/5 times -2 is -8/5. And, in class I always tell you, check my calculations. I do these in my head. Now I'm going to add 4 to each side. That looks much more reasonable. Let's see, 4/5 is 20/5. And so we have the tangent line. But we were talking about normal lines, so let's create the normal line for this. And for us, the normal line is a change in the slope. So slope normal is going to be 1 over the slope of the tangent, negative, which becomes -5/4. So that means our normal line is y minus y1 equals m normal, x minus x1. Our y1 is still 4. This is now -5/4. And our x is still 2. So y minus 4 equals -5/4. X plus, the 2's will cancel, so 5/2. 10/4, 5/2, yep. And then I'm going to add 4 to each side. Which is 8/2. So -5/4 x plus 13/2. And so we found a normal to this surface.